All right, it's time. Welcome back. Hope you had a good weekend. I hope that you saw our first homework assignment has been posted, so check it out. It's due tomorrow night, and please let me know if you got any questions. I'd be happy to help out. I wanted to start with another example. Actually, I wanted to start with an example that's kind of similar to one of the ones on the homework, so this might help you out. Or maybe you already did it. If you're like that, you like to do the homework early. Let's talk. We talking about topologies, of course, and at the end last time we had sort of a big kind of list of topologies. As far as topologies on R, the from finer to coarser, or from coarser to finer. I don't remember which way I wrote it around, but the finest of all is the discrete topology. This is one in which all possible sets are open. I think actually I wrote it the other way around. Can I put that over here. The finest, that's the finest. The coarsest is the trivial topology, in which no sets are open except the empty set and the whole space of X. And then there was the finite complement topology. That means a set is open when its complement is finite. And then all of those sets are also open in the standard topology. And those sets are all open in the discrete topology. All right. These are coarser, and these are finer. Finer because there are more open sets over here. The discrete topology, every set is open, whereas over here there are fewer open sets. Coarser and finer. All right. One thing that I probably should have said this on the first day of class, although I didn't. To be honest, I didn't notice it. I didn't take note until sometime over the weekend. As you are reading our book, they write the subset sign. Usually I would write, these are all proper subsets. So this means subset or equal, right? This is the standard terminology, or the meaning of that symbol as I write it. Actually, in our book, they never use that symbol at all in the book. This, without the little line, means subset or equal. I don't really like this, but this is the way that it's done in the book. So for instance, A subset of B means A is a subset or A equals B. But they don't put the little line. So ordinarily when I write this subset sign, I mean a proper subset. That is a subset, but it's not equal. But actually our book is not that way. I don't know if this is ever going to matter, but if you see this in a homework problem, it might matter from time to time. That in our book, the subset sign does allow the two sets to be equal. Slightly confusing in my opinion, but who am I to argue with the authors of our textbook, the wealthy authors of our textbook? All right, they probably don't see a lot of money from the ridiculous book prices. Okay, anyway, I wanted to talk about one more example of a topology on R, which is not any of these, but another fun example of a topology on R. There are many topologies that you could use on R. Another topology on R. You'll have some practice on the homework of dealing with, is this or is this not a topology, that kind of thing. Here's another topology on R. T. This one, as far as I know, doesn't have a fancy name to it. But anyway, it is the set of all things which it is either the empty set or all of R. Or, this is the interesting part, a topology must automatically include the empty set and also the entire space. These are the interesting open sets. The other open sets I'm going to use are any open intervals like this, but they have to go up to infinity. All right. So the open sets in this topological space, the open sets are, well, this or any open interval unbounded above, right? An open interval which goes up to infinity. Those are the open sets in this topology. So ordinary open intervals which are bounded, they don't count as open sets in this topology. All right. Could we demonstrate that this is a topology? I hope everybody remembers. Last week we talked at length about the three properties which make something a topology. So let's show it is a topology. There were three properties. Anybody remember the first one? This you should know on our first test, which is not soon. What?
The empty set and the whole space is in.
Yes, this is typically the easy one, and it's very easy in this example. We have to show that empty set and the whole space, which is R, are open. This is just by definition. I said so especially at the beginning that the empty set and R are declared to be open sets from the get-go. So there's nothing really to show for this particular one. In some examples, you might actually have to prove something for that, but typically it'll be easy. All right, the second one. What was the second property? Yeah.
With the finite intersections?
Yes, this is the finite intersections property. So we have to assume that we have some finite number of open sets. So I'm basically always going to structure it in this way. Let U1 up to UN be open. And then our job is to show that the intersection of all of those things is also open. Where in this case, open means they are intervals up to infinity, from some point to infinity. So it would be a good idea to say, okay, because they're open, I can say each of these UIs equals something like the interval from BI to infinity, right? That's what it means to be open in this topology. Or I suppose they could be empty, but then the intersection is empty anyway, so that it doesn't matter. It's not interesting to imagine them to be empty sets or the whole of R. All right. Then UI looks like that. And then what does the intersection of all of them look like? So we could think of this in terms of a picture maybe. Here's R, right? And I have several different open intervals which go all the way up to infinity. So there's like B, the first is like U1, which goes from, B1 up to infinity. B1 all the way up to infinity. And then maybe I have B2 all the way up to infinity. Maybe B3 is over here all the way up to infinity, right? There's only finitely many, so eventually they just stop. Bn maybe is over here, goes all the way up to infinity. If I take the intersection of all of those, is it still an interval which starts somewhere and goes up to infinity? I think it is. I mean, the way it looks on the picture, it seems to me that if you take the intersection of all of those, it looks like some interval which goes up to infinity. Can you say specifically what is the endpoint on the interval of the intersection? According to the picture, the intersection, I equals 1 to n of ui. Can we say, like, I want to actually just write it as an interval where this is something? Can you say what's the endpoint? Yeah?
Is it Bn?
Yeah, well, on my picture it's Bn because that's the one that's furthest to the right, right? That's really what matters. I mean, it may not be that the last one is actually the one furthest to the right. So can we say, like, there's some simple way of writing here? It's whichever one of these is furthest to the right. How would you write that?
B max.
Yeah, how about the maximum of the B's? I would write something like maximum of the BI, something like that. Right? That's the biggest of the B's is going to be the endpoint of the intersection of all of those intervals. All right? But anyway, since that is an interval, which is unbounded at the top, so this intersection of the UIs is open because it is some interval up to infinity. All right. This is the finite intersections property. All right. Why was it important that it's finite? Actually, it is kind of important that it's finite. If there were infinitely many of these sets, then maybe there wouldn't be a maximum. Maybe they would go up forever. Although it'd still be true, I think. Then even if there was no maximum here, then the intersection would just be the empty set, which is still an open set. But anyway, the finiteness, because I said max here, that relies on the fact there's only finitely many. All right, and the last property. So this was property number 2. How about property number 3? This is about unions, but any unions, not just finite unions. So this is the unions property. And for this one, again, I'm going to begin like this. Like up here, I started off like this. Let these be open. But it has to be any union, not just finite union, and not even just a countable union. The way that we're always going to write that is something like this. Let U alpha be open for alpha in A, where A is just some index set, we call it. The U alphas, there's just a lot of different U alphas. How many? Could be finitely many, could be infinitely many, could be uncountably many, it doesn't matter. It's just a whole bunch of open sets, all right? I'm going to try and do the same business, though, okay? Let's try and copy the steps that we did up there, only we're going to have to use a union at some point. So then UI is, again, because each of the U's are open, I can say then U alpha equals some interval, B alpha to infinity, right? Because that's what it means to be open in this example. I'm just copying the steps here. And then what does the union of all of them look like? Well, maybe I'll draw another picture, or it's really the same picture again here. What does the union look like? Does the union look like another interval going up to infinity? I think actually it does. So then the union, just using the same picture again, union of all alphas of U alpha. Can we write it as indeed an interval up to infinity? What do you think? If instead of intersecting, so in the first example, I took the intersection, which means it ended up being whichever one, the biggest one. What if I take the union instead? Yeah? It's the minimum. Yeah, this is actually, can I say, don't write this down yet, because it's not quite the min, but that's really what I would like to say, minimum of the B alphas. Because you want, instead of the one furthest to the right, you need to take the one furthest to the left in order to get the union. Anybody want to argue about the word min there? Oops. What's wrong with min? This is not necessarily a finite union, right? There could be infinitely many sets here. And that means that actually there might not be a minimum of these B's, right? The B's could be like an infinite sequence which goes down forever. Or the B's could be some weirder thing where maybe the B's approach a certain value but they don't ever actually equal that value. Then the minimum may not exist. Anybody want to suggest something we could use instead of the minimum? This is like something that you talk about a lot in real analysis. It's something that's kind of like the minimum of a set, but maybe the set doesn't actually have a minimum. Yeah. The inf. Yeah, I want to use the inf instead of the min. The min might not exist because there's infinitely many B alphas. The inf, though, I can use. I don't know if you're still worried. Is it true though that the inf always exists? No, I think the inf always exists as long as the set is bounded below, but maybe the set is unbounded below. So this, can I just say, as long as the inf of the B alphas exist. All right. If the inf doesn't exist, that would mean the B's actually, they just go down forever. The B's decrease without bound. In that case, actually, I think you need a special argument. What would the union be if the B's actually decrease forever? What would you actually get when you take the union of all of them? Yeah. Yeah, I think you'd get everything. Like all real numbers would be covered by the union if the inf doesn't exist. So I would say then this union equals that interval as long as the inf exists. If the inf does not exist, if the inf B alpha does not exist, that is to say the B alphas are not bounded below, then the big union is just all of R, all right? But in either case, it is an open set, right? In the first case, it's an open set because it's an interval up to infinity, which is open in our topology. And in the second case, it's the whole set, the whole space R, which is also open. So I will say either way, the union of the U alpha is open. Either because it's an interval up to infinity or because it is the whole set of R. All right. And that's what we wanted to show. Any thoughts about this one? This is showing that something is a topology. You've got to show the finite intersections and the unions property. Yeah.
I just had a question for the second part for the finite intersections.
Yes.
How, I don't know if it's a dumb question, but how do we know that there is a maximum for the BI? Like if it goes up to infinity, can't
Yeah.
be also?
This is not a dumb question. I heard a cute slogan this weekend. Which I never heard this before. The only stupid question is one that you never ask. You have questions, you should shout them out. Yeah, the max here is guaranteed to exist. Can anybody say why? Actually, I think I mentioned this before, but maybe, yeah?
It's finite.
Yeah, because this intersection is finite. So that means there's only like 10 of these. And so there's a biggest one.
Oh, okay.
Yeah, when there's a finite amount of numbers, then there will be a maximum. They can't go up to infinity if there's only finitely many of them. Whereas in this case, you really it's more complicated because it might be infinite. Yeah, great. Thank you for the question. All right. So you'll see some problems like this. Actually, one that's very much like this on the homework, and some that are not exactly the same but similar. All right. We are almost done with the first section of the book. We're talking about, this has all been in section 1.1 of the book. I had one more thing, and this is just a very basic bit of terminology. Basic terminology here. That this is a word that we're going to be using very often throughout the whole course. In a topological space, X, that is, remember, topological space just means some set X which has a topology on it. So when I say, let X be a topological space, you should imagine X is something like R with intervals as the open sets, but it could be something else. In a topological space X, with some point, X, little x in big X, if you look at a particular point, there is such a thing as a neighborhood of that point. Now, in real analysis, a neighborhood usually means like a very small epsilon neighborhood, but it doesn't always mean that in this case. But in a topological space X with X in X, a neighborhood of X is, the definition is very simple, is any open set U with X an element of U. So the word neighborhood doesn't actually mean it has to be really small. It just means it's an open set that that point is part of. All right? A neighborhood of X is any open set that includes that point. So for instance, in R with the standard topology, I could say something like 0 is, no, I want to say something is a neighborhood of 0. How about the interval -1 to 1 is a neighborhood. I'm always going to write neighborhood for neighborhood, just because I don't want to write that whole word. This is a neighborhood of 0, right? Neighborhood just means it's an open set which includes that point, all right? It doesn't have to be really small. It also doesn't have to be like symmetric. Like this as a neighborhood is somehow equally spaced on either side of that point 0, but it doesn't need to be. So also, 1 to 10 is also a neighborhood of 0, right? It just means that 0 is a point which is inside that, and that is an open set. Neighborhood means an open set which includes that point. All right, also, R is a neighborhood of 0, just an open set. How about this? Is the empty set a neighborhood of 0? No, because the point actually has to be in there for it to count as a neighborhood of 0. The empty set is an open set, but there are no points in there, so it's not a neighborhood of anything. All right? Great. That's the terminology of neighborhood. And there's an important sort of classical theorem. This you should recognize from real analysis, a theorem from real analysis about open sets and neighborhoods. Remember, in the standard topology that you talk about all semester long in a real analysis class, what is the definition of open set? Or at least the way that I always think about open set is, it means that every point in the set has an epsilon neighborhood around it, which is part of the whole set. I don't know if you remember these things from real analysis. I just had real analysis last semester, so I remember all of these things. Open set in real analysis means every point has a neighborhood which is contained inside that set. The same is actually true in any topological space. That fact is not a fact about the real numbers. It's actually a fact about any topological space. So it says, I'll start like this. Let X be any topological space. This is a theorem about all topological spaces. And I want to consider any subset of X, a subset of X. Then A is open if and only if every point has a neighborhood which is contained in A. That's what I'm going to write here. So I'm going to say something like, for all X in A, there exists U, an open set. Well, really what I should say is a neighborhood of X. Sorry about that. A neighborhood of X. That means it's an open set and it includes the point X, such that A is a subset. No, U is a subset of A. I wrote it backwards. All right. That's what it means to be an open set, is that every point has a neighborhood where that neighborhood is inside that set. So in real analysis, what this looks like is something like, if I have a big set, what it means for that set to be open is when I look at a point X, I can find an epsilon neighborhood around it, which is completely inside of the big set. And that is what the theorem says. It's the same thing. Only the neighborhood doesn't have to be like, in real analysis, you think of this neighborhood as some like itty-bitty small neighborhood. It may not be the case in a general topological space. It's just some neighborhood, though. All right. I would like to try and go through this theorem. The proof is not very difficult. First of all, it is an if and only if, right? That means you got to prove two directions. So we have to, first of all, assume A is open and prove that other stuff. And then secondly, assume that other stuff and then prove that A is an open set. So let's do the first way around first. This is like that direction, I'm going to assume A is open. And then we have to prove that other stuff. So that is to say, I let X be any point in A, and then we'll find U, a neighborhood of X, with U subset or equal to A, right? This actually is, this part of the proof is kind of stupidly easy, so easy that it might seem foolish to you. But anyway, I'm going to try and draw a picture here. So here is X, and A, we are assuming A is an open set. Maybe I'll just sort of scribble that in as A. We are assuming that A is an open set. Our job is to find a neighborhood of X, which is a subset or equal to A. Anybody have an idea? Can you find a neighborhood of X? Remember, neighborhood of X just means some open set which X is part of. Yeah?
Isn't that in the definition of A being open?
Yes, A is an open set. So it's, yeah, if you're feeling like this is kind of stupid, you are right. Can you tell me an open set which X is part of? The answer is A. I think I see it on your faces. Yeah. So is there a neighborhood of X that is a subset or equal to A? Yes, it's A, right? Actually, A is kind of the only thing it could be, just because you don't know anything else about anything in this example. There's no other way you could cook up some open set. All you know about is this set A. But anyway, yeah, that's the whole answer here. So I'm going to say let U equal A. Then U is open, because I said A is open, and U is A. And X is an element of U, because U equals A, right? And X is an element of A. So U is a neighborhood of X. Great. You can always just take the entire thing to be the neighborhood. The neighborhood doesn't have to be itty-bitty small, okay? The other part of the proof is the more interesting part, where you actually have to kind of say something, all right? Let's try the other part, all right? So this part is, I assume that for all X in A, there exists a open set U, a neighborhood of X, all right? So actually, this assumption is not just about a single neighborhood, but it means I'm assuming that for every point, every point has its own neighborhood, little neighborhood maybe, or they could be big, all right? Every point has a neighborhood. So actually, it's going to be more convenient to say, I'm going to write, let's call it UX as the neighborhood of X. Oh, and I should say with U subset of A, right? That's the important thing about this, is that the neighborhood is a subset or possibly equal to A, all right? UX subset or equal to A, all right? So this means every point has a neighborhood which is inside of A. So if my picture this time is like, if the red set is my set A, what I'm saying is, every single point here, X, there's tons of them, they all have little neighborhoods around them. And all of these neighborhoods are fully contained in A, all right? These are the UXs, are those intervals, all right? This is a point X, and every X carries with it a neighborhood, UX. And all of the neighborhoods are a subset of A, all right? What we have to show is that A is open. I want to show A is open, right? Because that's what the other side of this if and only if is about, showing that A is open. All right. Now, how can we show something is open in a topological space? Of course, in real analysis, open always boils down to some kind of epsilon something. But in a topological space, the only way that makes something open is if it's an intersection, a finite intersection of opens, or if it's some union of opens, all right? And I think actually my set A here naturally looks like a union of all these little neighborhoods, right? Now, what I drew here, those little neighborhoods don't actually cover up the whole set A. But actually, there's a neighborhood around every point. So if, every single point in here has its own neighborhood around it. Even the points right next to the other points, which are inside of the other neighborhoods, they themselves have little neighborhoods around them, all right? Every point in A has a little neighborhood around it. If I take the union of all of those, like this, all right? The union of all of those. This certainly includes all of the original points. It's if anything more than all the original points, because every one of the original points is one of those little neighborhoods, right? So when I take this union, this contains every x in A, right? Because ux always contains x. So if I union together all of those intervals, all of those little neighborhoods, certainly I catch all the individual points. But could this be any bigger than the set of A, right? This includes all of A, so maybe this, let me just say it that way around. A is a subset of that, right? The big union. Because that big union includes every point of A, right? Say, I meant to write so. So, A is a subset of the union. I actually need to show, I would like to show that A equals the union, because this union will be an open set. Could A be any bigger? I think actually A equals the union because each of the U's are a subset of the A, right? That means when I take this union, I never get anything bigger than A, because it's a union of things, all of which are subsets of A. All right? Since ux is a subset of A, this big union of ux is also a subset of A. I took a bunch of things, all of whom are inside of A, and take their union. The whole union is also part of A. All right? What have I said? Put these two things together. It means that A equals the union of all of the neighborhoods. And so A is open by the union's property of a topological space. Because the ux's are open, so their union, which is A, is also open. The end. All right. Can you remember what the theorem said? An open set is one for which every point has a neighborhood inside the set. All right? Just like in real analysis, it is true in any topological space. Any thoughts about that? And this is actually going to be a theme for this course, is sort of taking facts that you know from analysis and other things, and realizing actually some of those theorems from real analysis were not really about the real numbers. They were actually topological theorems, not just analysis type theorems. All right. Excellent. This is the end of section 1.1 in the book. I don't know if you care about the sections, but let's talk about the next section. Is a little bit, we are going to eventually talk about many different ways of defining topologies on different sets, and there is a convenient way to define a topology. Like this, right? That's how you spell convenient, I think. A convenient way to define a topology is in terms of what we call a basis for a topology. A basis for a topology. Everybody knows what is a basis for a vector space? If you're taking the comprehensive exam this weekend, I hope you know what a basis for a vector space is. Are you all taking the comp this year? Are you all seniors? Not everybody. All right. you won't all have the pleasure. But anyway, you should, even if you're not taking the comp this weekend, you should know what the basis for topology. No, you should know. Remember, the basis of a vector space is like, of course, a vector space like Rn has infinitely many vectors in it, but there are some like special ones, the basis vectors, which you can use to create any of the other vectors by adding them together and scaling them. That's the point of a basis in a vector space. And the same idea is what, it's the same idea for a basis for a topology. So a basis for a topology is a, I will say, parenthetically, a smaller set of open sets which are used to build any open set. All right. Like when I've been speaking informally, I've said many times the standard topology for R is the one that you get using open intervals. All right. But and I hope that you all agree with that. Really, to say it technically, the open intervals are a basis for the topology on R, and any open set in R can be written as a union of open intervals. All right. It's not that any open set is an open interval. In R, any open set is a union of open intervals. And so in the standard topology, R with the standard topology, the open intervals form a basis for the topology. This is because since any open set in R in the standard topology is a union of open intervals. This is a true fact from analysis. All right. This is the idea of what it means to be a basis for a topology. It's some kind of smaller bunch of open sets. They're not the only open sets, but all the other open sets you can make them by unions of the basis open sets. All right. This is kind of like, it's also like a generating set in algebra, like in a group, the set of generators of a group. It's not all of the elements of the group are generators, but if you have the generators, you can make any other element of the group by multiplying the generators together. And this is a similar idea to that. Not all the open sets are in the basis, but if you start with the basis open sets, you can make any other open set by combining them together. All right, this is the idea. Now, not any set can be a basis. Just like in linear algebra, not any set of vectors can be a basis. A basis in linear algebra, they have to be linearly independent and the span has to equal the entire space. There is a similar sort of thing about what is allowed to be a basis in a topology. And in order for this to work, it's sort of automatically, when I say any open set is a union of the basis sets, this will automatically work for any set or any basis set just because any union of open sets is going to be an open set anyway. But I haven't said anything about the intersection. So I'm going to say to be a basis or to work as a basis, the basis needs some nice intersections property. There actually is not a requirement in terms of unions because the point of the basis is to make all kinds of unions anyways with the basis elements. But what is important is it is necessary to have some nice intersections property. All right, but anyway, so I'll give you the formal definition of what it means to be a basis. It is just basically going to say it's some bunch of open sets where you can make the whole space using those open sets, and they have some kind of nice intersections property, which you'll see in a moment. But anyway, a basis, generally speaking, I'll write this as a real definition here. So I'll say let X be a topological space with topology T. All right, so T refers to all of the open sets. Now, a basis is just a collection of some nice open sets, not all of them, but just some of them. So a set B, which is a subset of T. This is my fancy B. I hope you can write a fancy B, because I'm also going to write a normal looking B. There's a lot of fonts in topology. So T refers to all of the open sets. B refers to only some of them. We're going to call them a basis. So a set B, a subset there, is a basis for a topology when it has these two properties. Number one, first of all, you have to actually be able to get every point of X by using sets from the basis. So this just says, this is the simpler property. For all X in X, there exists a basis open set with X in B. All right? So every point in the whole space is actually part of one of these special open sets, which is going to be part of the basis. All right? That is, you could say, sort of in ordinary language, you could say the B, the basis, covers X. Actually, this is literally like, if you recall from analysis, there was a concept of an open cover. This is the same thing. It just says that every point in the space actually is part of one of these basis open sets. All right? And then the second property is a little weird. You could also think of this as analogous to, in linear algebra, a basis. The span of the basis has to be the entire vector space. That's a similar idea that here these basis open sets have to actually cover the whole space. And the second one is this weird intersections property, and I will write this down and then talk a little bit about what it means. If B1 and B2 are two different sets in your basis with some point in the intersection, then there is another set. Yeah, I just got to write this, and then we'll explain what it means. Another basis set with X in B3, and B3 is a subset of B1 intersect B2. All right? This is the weird intersections property for a basis. This slogan does not appear in our book, but basically I think of this as this is like the shrinkable property. The basis sets are shrinkable in this sense. Can I draw a picture which represents all of that business that I wrote there? If B1 and B2 are basis open sets, so I will just draw them as, maybe like this, and they have some intersection. Here's B1 and B2, and they have an intersection, and that intersection includes some point X. Then it says there exists another basis set with X in B3, and B3 is part of the intersection. So it means this. There's always another set in the basis which is inside the intersection. And this is why I call it the shrinkable property. If you have two sort of bigger sets in the basis and they have some overlap, then that overlap includes another set in the basis. All right. This kind of means the basis sets are closed under intersections. If you have two basis open sets, then there's another one which is inside their intersection. It doesn't literally mean it's closed under intersections. It doesn't say that the intersection equals one of the basis sets. It says that there's another basis set inside the intersection. All right. This is the shrinkable property. If you have two big basis sets and they intersect, then there's a smaller one. All right? This, you know, the analogy but with the real numbers, this is definitely true in the real numbers. If I have, say, in R, 2 open sets, which I think of as being 2 open intervals, right? Say one here and another one here. I'm thinking of this interval here intersecting with this interval here. Do you agree that there actually is an open interval inside the intersection? Yeah, there is. You know, you can make a smaller open interval inside the intersection of these 2 bigger open intervals. This is the fact that is necessary to be legal for a basis. If you have 2 big open sets and they intersect, there has to be another one of the basis sets inside the intersection. All right? This is how basis sets need to work. If this property is not satisfied, then it doesn't make sense to take unions of everything and make a topology out of it. All right. This is what it means to be a basis for a topology. We got 5 minutes. I thought, let's see if we can actually write out the details demonstrating that the open intervals are a basis for the standard topology in R. I think we can do this. So I'll write this as a theorem. The open intervals in R are a basis for a topology. Both parts are pretty easy. Actually, the second part is basically what I just said up here. So, but the open intervals in R are a basis for a topology. All right? So we got to show the 2 properties of a basis. The first property, if you recall, was for all x in X, there is some basis set where X is in B. So what I have to show here is, you know, let X be in my space is R, and I want to find, we'll find a basis set B with X in B, where in this example, basis set means open interval, right? Because I'm talking about the open intervals. Can anyone tell me, if you have a real number x, is it true that x is an element of some open interval? That's what I'm saying here. I think the answer is yes. So for any x, x is an element of, can anyone say, like specifically? Give me an open interval that x is an element of. Yeah? All right, he took the nuclear option. I was expecting one of 2 answers. This is one of them. The other answer I would have expected is this. That's an open interval which X is a part of, right? Of course, there are many, many other things you could have said, although these are the only 2 sort of obvious things to say, I think. You could also say the interval from x minus pi over 2 to x plus 1,000 or something like that. It doesn't matter, but it's definitely true. Every point in R is an element of an open interval. Okay, so that was the first property, that every point in the set has to be an element of one of the basis sets. And then the second property is this weird intersections property. But if you believed this picture that I drew up here, it is true of open intervals in R. So what I have to do is I take B1 and B2 open intervals with X in the intersection B1 intersect B2, all right? So the picture, if they're open intervals, maybe I will just, for the sake of writing them, let's say B1 is the interval A1 to B1, and B2 is the interval A2 to B2, right? Those are the endpoints. They are open intervals. And because they have some point in the intersection, the picture must look something like this. Let's say this is A1 to B1, and then the other one is like here, A2 to B2, all right? And X would be a specific value in the intersection. This is what the picture looks like. What we must demonstrate is that there is an open set, an open interval, which includes X, which is part of the intersection. So we must find we need X to be an element of, say, B3, which is a subset of the intersection, B1 intersect B2. We can use B3 equal. Can anybody say what should the B3 be? It's meant to be an interval containing X, which is part of the intersection. Yeah.
A2 to B1?
A2 to B1, yeah. The open interval A2 to B1. Then X is in B3, and B3 is a subset of B1 intersect B2, as desired. That's it. All right. So the open intervals do form a basis for a topology. And that's about it for today. Thank you for your attention. We'll talk more about bases next time. Please check out the homework and let me know if you have questions. I would be happy to chat about it. I always have office hours scheduled right before and right after class, although it's only briefly. I have another class at 12:30, but we can talk until then if you ever want to. All right. See you later.